we solve some exercises regarding metric, and these exercises are you can find in the book Metric Spaces by Michael O. Searcoid. This is the book, and you can find these questions, these exercises in this book in chapter number 1. So first, my first question is that suppose X is a set and D from X cross X to R. Here R is a set of real numbers. This is a map, and X cross S is the Cartesian product. Show that D is a metric on X if and only for all a, b, z belongs to X. The two conditions D of a, b is equal to 0 if and only if a is equal to b, and the second condition D of a, b less than or equal to D of z a plus D of z b are both satisfied. So this is the first question. We show that D is a metric on X if and only if this condition and this condition, both of them are satisfied. So first of all, we assume that for all a, b and z belongs to X, D of AB is equal to 0 if and only if A is equal to B, and D of AB is less than or equal to D of ZA plus D of ZB. This is our assumption, and we prove that D is a metric on X. The first property of non-negativity uh, for the map D, we prove the negativity. We prove that the non-negativity of the map D to prove D a metric on X. For all a, b, z belongs to X, we have that D of AB less than or equal to D of ZA plus D of ZB. So in this inequality, because it is satisfied here, we assume that this inequality satisfies for all a, b, z belongs to X. So in this inequality, we put B is equal to A, and we get B is equal to A, and we get A A D of AA less than or equal to D of ZA plus D of ZA again. And as we know that by the assumption that if A and B they are equal, then D of AB is equal to 0. So by this assumption, D of AA that's equal to 0, and this is less than or equal to, this one is a real number and this one is also a real number. Both of them are real numbers. So when we add them, we get 2 times D of ZA. Then we get 0 is less than or equal to D of ZA by dividing 2 on both sides, and this holds for all ZA belongs to X. So this is the first property of non-negativity for D. The second one, we prove that uh, D of AB is equal to 0 if and only if A is equal to B. This is the second property for a metric, and with the assumption, by using the assumption, this is evident, this is obvious that D of AB is equal to 0 if and only if A is equal to B. You can see here So the second property for a metric is uh, evident here. So we can say that the second property is evident. So you just write here the second property is evident. So we no need to prove here. The third property is that d of AB is equal to d of BA. And the third property, which is called the symmetric property. So we prove the third property here, um, since we um, actually we use the assumption here, this one, d of AB is less than or equal to d of ZA plus d of ZB. So by using this inequality, we can write here d of AB is less than or equal to d of BA plus d of BB, where we put Z is equal to B on right hand side. Z is equal to B, then we get d of AB less than or equal to d of BA plus d of BB. In this inequality, we just put Z is equal to B, then we get this inequality, this one, and that's equal to d of AB, which is less than or equal to d of BA plus 0. By this assumption, d of BB is equal to 0, and we get d of AB less than or equal to d of BB, sorry, d of BA. That's equal to, you can say this is the inequality 1. And uh, if we put B is equal to something like that, yes, uh, if we start from here, d of BA, and we put Z is equal to A in this inequality, then we get d of AA plus d of AB, because this inequality holds for all A, B, Z belongs to X. So we just put Z is equal to, means what is Z here? Z is the element A. Okay, so uh, by using this inequality, we have d of AB, d of BA, which is less than or equal to d of AA plus d of AB. So here that's equal to Z and that's equal to Z. Hence we have d of BA less than or equal to 0 plus d of AB, and this is equal to d of BA less than or equal to d of AB. This is our inequality number 2. By using 1 and 2, you can see here d of AB less than or equal to d of BA, and here d of BA less than or equal to d of AB. By using 1 and 2, 1 and 2 implies both d of AB and d of BA are equal. So this is the symmetric property for the map D. This is the third property for a matrix which has been proved. Now for the triangle inequality, we prove the triangle inequality. If we start from here, you can see for all A, B, C, belongs to X. D of A, B less than or equal to D of CA plus D of CB. What is uh, what is the reason here? Because we use this inequality, and here this inequality holds for all abz belongs to X. So we use this inequality and we write in this way, where z is equal to c. So we can write here d of ab less than or equal to d of ca plus d of cb. And we know that that's equal to d of ac by using the third property, because d of ca is equal to d of ac plus d of cb. So this is the triangle inequality, which is d of ab, which is less than or equal to d of ac plus d of cb. So this is our required triangle inequality, and hence d is a metric on X. Now we assume that d is a metric on X. Conversely, suppose that d is a metric on X. And we prove the two conditions here, this one and this one. Since d is a metric on X, so by the third property of metric, we have d of a b that's equal to 0 if and only if a is equal to b. So the first condition is proved. And if we talk about the second condition, what we have, by triangle inequality, for all a b z, for all a b and z belongs to X, by triangle inequality, d of ab, which is less than or equal to d of a z plus d of z b. And since d is a metric, so by symmetric property, that's equal to d of za, this is equal to d of za by the property of a metric, because d is a metric. Thus d of zb. So this is the second condition, that d of ab, which is less than or equal to d of za plus d of zb. So this is our second condition. Hence we have proved the converse here. So this completes the proof. Now the second exercise, we come to the second exercise, which is, suppose that d is a metric on X. Prove that the inequality mod of d of xy minus d of zw is less than or equal to d of xz plus d of yw, which holds for all w x y z belongs to X. So we prove this inequality for all w x y z belongs to X. Actually, uh, we use the property that for all real numbers, mod of x minus a is less than or equal to L. If this one holds, if we prove that a minus L less than or equal to x, and that is less than or equal to a plus x, a plus L, then we have x minus a mod, which is less than or equal to uh, yes, L. So we use this implication that if we have a minus L less than or equal to x, and x is less than or equal to a plus L, then we have mod of x minus a less than or equal to L. So we use this implication, and we we prove that this one holds. You may name this one as one. So d of zw is less than or equal to d of zx plus d of xw, because d is a metric, and by triangle inequality we can write here d of zw less than or equal to d of zx plus d of xw, and this one is less than or equal to d of uh, zx. By applying again the triangle inequality for d of xw, which will be less than or equal to, because d of xw is less than or equal to, uh, for example, if I write here separately d of xw, this is less than or equal to d of x y plus d of y yw. Okay, so uh, we can apply the triangle inequality for d of xw, which is less than or equal to this expression d of xy plus d of yw. So it means that the whole expression d of zx plus d of xw, which is less than or equal to d of zx plus d of xy plus d of yw, because we apply the triangle inequality uh, on this d of xw, and what we have, this implies that d of zw less than or equal to d of zx plus d of x y plus d of y w, and this implies that d of zw minus d of zx minus d of y w, which is less than or equal to d of xy. And when we take minus outside, minus 1 outside, so by taking minus 1 outside, we have this expression. So this is named as 2. Now d of xy, which is less than or equal to d of xz plus d of zy, because we use the triangle inequality, and again by using triangle inequality for d of zy, same as above, in the similar way as we have done above, we have d of x z plus d of zw plus d of w y, because we use the triangle inequality for d of zy, which is less than or equal to d of cw plus d of wy. So it means that this is less than or equal to d of zw plus d of x z plus d of y w, and this is named as 3. So if we see, we have you can see here, uh, this is, if we see this inequality, a minus l is less than or equal to x. So this is our a minus, and this is our l, which is less than or equal to x. So this is a minus l less than or equal to x, and if we see, x is less than or equal to a plus l. So this is our x, which is less than or equal to, this is our a plus this is our l. So combining 2 and 3, we have d of zw minus d of zx plus d of yw, which is less than or equal to d of xy, which is, by using 3, which is less than or equal to d of zw plus d of xz plus d of yw. Here you can write here, because d of zx is equal to d of xz, so we can write here also d of xz, because d is a metric. So we see that d of zw minus d of xz plus d of yw, which is less than or equal to d of xy, which is less than or equal to d of zw plus d of xz plus d of yw. If we see our uh, the implication 1, if we see this inequality, a minus l is less than or equal to x, and x is less than or equal to a plus l, so you will come to know that this is a minus l less than or equal to x, which is less than or equal to a plus l, because this one and this one, they both are equal. So By using one, we can write, by using the implication one, we can write in this way that mod of d xy minus d of zw, which is equal to a, and this one is equal to x. So x minus a mod, which is less than or equal to L. And what is L? L is d of x z plus d of yw. So this is our required inequality. We will check again that whether it is true or not. You can see here d of xy minus d of zw, which is the mod of d of xy minus d of zw less than or equal to d of xz plus d of yw. Now we solve the third exercise. Our third exercise is, suppose Z is a set and XD is a metric space, and f from Z to X is an injective function. Injective means one-to-one function. Then show that the map, you can see uh, the map you can see here. We name this map uh, D dash, uh, which maps AB to D of FA FB. Okay, so we show that this map D dash is a metric on Z. Okay, so we show that this map is a metric on Z, where AB where AB uh, how to say, they are the elements of Z, and f of A and f of B, they are the elements of X, and D is a metric on X. Okay, so we use the also because here to prove that this map is a metric on Z, uh, we will also use the uh, injectivity of f, where f is from Z to X. So we use this function f, that f is an injection, f is one to one. We use the property of f, which is one to one, to prove that this map is a metric on Z. So we will see that how we can use that f is an onto function. Sorry, f is a one-to-one function. How to use that f is a one-to-one function to prove that this map is a metric on Z. This map. So here uh, if we name this map, we name the map AB, which maps to D of f of A, f of B. We name this map by this as D dash. Okay, and we show that to show d dash is a metric on C. The first property is for the non-negativity of d dash. What we do, since for all AB belongs to Z, we have f of A and f of B. They both belongs to X, and d of the distance of f of A, f of B with respect to the metric D is obviously non-negative. Since this is non-negative, so and it means that because uh, this one is equal to d dash of AB. Okay, so by using uh, so this one also, it means this is equal to d dash of AB, because we name this map as d dash. Hence hence d dash of AB, which is equal to d of f of A plus uh, d of f of A, f of B. This is non-negative. Okay, because this is equal to d dash of AB, because we name this map as d dash. Hence the non-negativity of d dash is proved. Now if d dash of AB is equal to 0, then d dash of AB is equal to 0. It means that d of f of A, f of B, that's equal to 0. Then since d is a metric, so both f of A is equal to f of B by the property of a metric. And since f is injective, f is one-to-one function, so what does it mean? It means that if we have f of A is equal to f of B, then 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 the pre-images A and B, they are equal. Hence we have proved that if d dash of AB is equal to 0, then we have A and B equal. And for the converse, if A is equal to B, since f is a map and AB belongs to Z, since f is a map and AB belongs to B, AB belongs to Z, and A and B both are equal, so we can write here f of A is equal to f of B, because f is well defined. F is a map, and the uh, map is obviously a well defined relation. So by the means that f is a map and f is definitely well defined. So what does it mean? If A and B both are equal, then the image is f of A f of b, they are also equal. And since d is a metric and f of a, f of b belongs to x and d is a metric on x, then we have, by the property of a metric, d of a b, d of f of ab, sorry, d of f of a, f of b is equal to 0. By the property of a metric, we have d of f of a, f of b, that's equal to 0 because they both are equal. And this is equal to d dash of ab. So d dash of ab, they both are that's equal to 0. So we have proved that d dash of ab is equal to 0 if and only if is equal to b. And the third property, which is the symmetric property for the map d dash, you can easily prove that d dash of ab, which is equal to d dash of b. So this is not so difficult, and this is quite handy. You can prove that d dash of ab equals to d dash of ba. So I won't elaborate for the third property. You may try by yourself. That's not so difficult. So for the triangle inequality for all a, b, c belongs to z, for all a, b, c belongs to z, d dash of a, c, that's equal to d of f of a, f of c. Okay. And since b belongs to z, so f of b belongs to x. Okay. So uh, by the triangle inequality for the metric d, because d is a metric on x, and f of b belongs to x. So by the triangle inequality, both are the elements of x, the both f of a and f of c, both are the elements of x. So by using the triangle inequality, we can write here d of f of a, f of b plus d of f of b, f of c. And this one is equal to d dash of ab, and this one is equal to d dash of bc. Hence we have d dash of ab plus d dash of bc. Therefore d dash is a metric on z. So this is our